In this video, I want to illustrate how to design a Moore circuit to realize a sequence detector. So if you recall from the previous lecture, we were talking about a sequence detector which takes in a stream of bits, one bit at a time. Those are clocked in sequentially, and we were looking for a particular pattern. And in the last lecture, we developed a sequence detector that was a Mealy circuit to find the sequence 101 at any point in the pattern of bits that were coming in. And it does not reset, so the last one that is received could be the first one of a new 101 sequence. And so here is an example sequence. Here we see 101, so the output Z is 1, indicating we found the pattern. Here we have another 101 found, so we have an output of 1 here. And this one is the beginning of another 101, so we see the output 1 here. And so previously we had derived this Mealy state transition diagram. And so with this we had 3 states. The first one indicated that we were at our initial state. We had not yet received the first 1 in the sequence. State S1 indicated that we had received a 1 and we didn't know what the next 2 bits would be. It could be the 0 and 1, but at least we're 1 bit in to finding the sequence of interest. And then state S2 indicated that we had a history in the last 2 bits of 1 and 0 received, and if we get a 1 on the next bit, then we did find our sequence and we output a 1 as we indicate here. If we get a 0, then that means the last 3 bits were 1, 0, 0. That makes no progress toward finding 101, and we reset all the way back to our initial state. So now we are going to redesign this as a Moore circuit. We may need to add some states to do so, because you'll notice here in S2 you have 2 different transitions. One that puts an output of 0 and one that puts an output of 1. Some of these states may still be able to be used in the Moore implementation, and so we'll see as we go through deriving this. And then what we're going to do is we are going to implement this using various other flip-flop logic. So if you recall in the previous lecture we derived D flip-flop logic. In this lecture we're going to get into T flip-flop, SR flip-flop, and JK flip-flop logic to realize this sequence detector. So this was our previous binary state representation. We had 3 states and we had chosen this binary, and we had gone through and determined our logic for A plus, B plus, and Z, and we had implemented it as a D flip-flop. So this was our Mealy implementation. We're going to again repeat this same process for Moore. So let's convert it, and we're going to recall that the Moore outputs are solely dependent upon states. So some of the states are going to be exactly the same as what we had in the Mealy. So let's look at the states that we might be able to reuse, or the states that we had previously. Remember, the S0 means that we haven't yet detected a 1. S1 means that a 1 was detected. We don't know if the next 2 bits are going to be 0 and 1 or not, but we're at least 1 bit in. And S2 indicates that the last 2 inputs were 1 and 0. And all of these states output a 0 until we get the 3rd bit in. So in fact, we can start with these 3 states. S0 is still going to indicate that it is the initial state, and if we get zeros we're going to transition back. And because it's a Moore, we're now going to put the output inside of our state circle. We are not going to label it on these transition arcs. And so S0 is still our initial state, meaning we've only gotten zeros thus far, or at least in the most recent history we've only gotten zeros, and we haven't yet made progress along the 101. If the last bit was a 1, that takes us over here to S1, and then if we had the last bit was a 1 and now we have a 0, that takes us to S2, indicating that we are now at 1 and 0 for the last 2 bits. And if we get in a 1, we can transition to a state that will output a 1. If not, we'll have to figure out where we transition. So when we detect the 3rd bit in the Mealy machine, what we did was we went from S2 back to S1 and we output a 1. So what that meant was we had 101 completed and that last one that we picked up could be the beginning of a new 101 sequence. We still have a very similar approach here, but we will see that it's slightly different because we cannot simply output a 1 for different inputs. So the Mealy gives us a little bit more flexibility. The Moore is going to have some tighter restrictions on when certain outputs can happen, and that can only happen when we change states. So none of the states that we've put in currently output a 1. So we're going to add an S3 state to be the state that indicates we have received 101 as our last 3 bits, so we have detected the sequence. And obviously the output here would be a 1, indicating that we've found it. So here we now have 4 states, S0, S1, S2, and S3. And so as we transition through, we see if we get 1, 0, 1, we now output a 1. And so now what's left to do, because this is incomplete, is to fill in all of our other transitions. So right now we have both a 0 and a 1 transition for S0. We have a 0 transition for S1. We need to figure out what are we going to do if we're in S1 and we get another 1. That will be very similar to what we did in the Mealy circuit. In fact, we will have it exactly the same. It will just transition back to itself. And then if we get down in here to S2, we have the 1 transition, but what do we do if we get another 0? Well, we might do exactly what we did in the Mealy and go back to S0. And then if we're in S3, we don't have any transitions right now. So let's go ahead and derive some of that logic. So we already have both the transitions from S0, and the question is, what should we do when we're in S1 and we get a 1 input? Well, we're going to transition back to ourselves. And what should we do when we're in S2? Well, as we just said, we can go from S2 to S0. And then, if we look at our history, when we're in S3 and we get in a 1 input, our last 4 bits will be 1, 0, 1, 1. Well, that last 1 that we get in there could be the beginning of another sequence, so we can transition over to S1 to indicate that would be the start there. And then what do we do if we get a 0? Well, that would mean our last 4 bits would be 1, 0, 1, 0. In that case, then we might be 2 bits into the sequence. We might be at 1, 0, and then potentially going to another 1. So in that case, we can transition over to S2. And that way, that would indicate that we already have our 1 and our 0, and all we're lacking is a 1 of finding the sequence. So this is our state transition diagram. Let's inspect it and make sure we have all of our states in there with outputs. We have S0, 1, 2, and 3 all have outputs labeled. And let's make sure we have all of our transitions. We have a 0 and a 1 transition for S0. We have a 0 and a 1 transition for S1. We have a 0 and a 1 transition for S2. And we have a 0 and a 1 transition for S3. And so now we have a complete state transition diagram. We know it is complete because all of the states have their 2 required transitions because we just have a single input. Remember, if it was multi-input, then we would have 2 to the n for however many n inputs we have transition arcs. But in this case, it's just 1 input, 1 bit coming in. And so we have our 2 transitions, and all of our transitions go to states that are already in the diagram. And so there's no need for additional states, no need for additional transitions, and we are done. And so now what we're going to do is take this diagram and translate it into a state table. And so we have this, and we're going to label our 4 present states down the left-hand side. And so we have S0, S1, S2, and S3. And then we're going to indicate our next state. So when we're in S0, we also are going to indicate our outputs. And in this case, we don't have to, as we go to transitions and then go to outputs, label them in pairs. We can already just put our outputs on there because we can read those straight from the state circles. So S0 outputs a 0, S1 and S2 output 0, and the only state that outputs a 1 is this S3. Now we'll just do our transitions based on the transition arc. So if we're in S0 and we get in a 0, we're going to stay in S0. If we get in a 1, we're going to go to S1. If we're in S1 and we get a 0, we go to S2. If we're in S1 and we get in a 1, we stay in S1. If we're in S2 and we get in a 0, we go back to S0. If we're in S2 and we get a 1, we go to S3. And then if we're in S3 and we get a 0, we go to S2. And if we're in S3 and we get a 1, we go to S1. So now we have our state table. And from here, it's a matter of choosing binary for each of the states. Now, we have 4 states, and so what that means is we need 4 binary representations, and so we can just use 2 bits to do that. And so in the previous example that we had gone through with developing a Mealy circuit, we only needed 3 states, so we still also used 2-bit binary, but as it turned out in that example, we did not use all 4 of the combinations. In this case, because we have 4 bits, we're using all of the binary combinations that are available to us with 2-bit binary. If we had one more state, we would have to add a whole nother flip-flop, and with that we would have to add an extra bit to our present state representation. So here we have arbitrarily chosen S0 to be 0, 0, S1 to be 0, 1, S2 to be 1, 1, and S3 to be 1, 0. We've really just chosen this gray code just so that it fits well in the Carnot maps, which we will deal with later. And so now it's a matter of find and replace. So everywhere you see S0, you're going to put 0, 0. Everywhere you see S1, you're going to put 0, 1, etc. And so S0 gets replaced by 0, 0. S1 gets replaced by 0, 1. S2 gets a 1, 1. S1 gets a 0, 1. S0 gets 0, 0, S3 gets 1, 0, S2 gets 1, 1, and S1 gets 0, 1. So we're just looking for each of these states we're transitioning to, and now we're putting our binary. And so we're going to do very similar things in terms of deriving the circuit using K-maps as we did previously. We can also see fairly obviously that the output is simply A and B prime. So that is just the last entry there. You could put that in a little 2-variable Carnot map based on A and B, but by inspection we can just find that the logic for Z is A, B prime. So we can do D flip-flops, and so that's nice and easy. We just take this and we can fill in from our current output of where we want to go next. So in this case, we just take this. This is where we are trying to put in dA, which is the same as A plus. So our left column, where x is equal to 0, is 0, 1, 0, 1. And so we're just going to copy that into the K-map. Then we'll go over here to the x equal 1 column and again copy the left column there. And then we'll do the same thing for our dB. And so over here we'll copy our 0, 1, 0, 1. And then we will copy our 1, 1, 0, 1. And so from there we can derive our logic. Oops. And so let's go ahead and see how we would circle things. And so I'm going to transition to a digital pen. Unfortunately, none of these have neighbors. So we have to circle them each individually. And so in this case, this would be x prime, a prime, b. So we get x prime, a prime, b, or xab, or then we have down here x prime, a, b prime. Okay, and then over here we can do 3 groups. Here's one, here's one, and then here's one. So our 3 groups of 2, this top one is going to be xa prime. And then this one is going to be a prime b. And then the bottom row is going to be A, B prime. And actually, as it turns out, these right two terms are just the same as A exclusive OR B. So you could have A XOR, which will indicate with a plus inside the circle, and B. So this is our logic if we chose to implement this with D flip-flops. Now let's see what it would look like if we were to implement it with T flip-flops. So if we go over here to T flip-flops, now we're going to use the same table. And remember, with T flip-flops, we're looking at our current A relative to our A plus, and if anything flips, anything changes value, then we're going to put a 1 into T. And if it stays the same, we're going to put zeros. So if we look over here at our A relative to our A plus in this case, we see that the values that change are these two middle ones. We go from a 0 to a 1 and a 1 to a 0. The top and the bottom values stay the same. And then we look at our x equal 1 column over here, and we see that again the middle two are the ones that change. And going over to our B, looking at the rightmost column, we see that we have a change in the bottom two. The top two stay the same. And then we have a change in all except for the second row in the B column for x equal 1. And so we can once again circle our groups here. And so we will circle this group right here. And so TA is simply B. And then down here we can circle this group of 4 right there. And so that's going to be A. And then we can circle this one top and bottom there, and that's going to be X B prime. Alright, so our logic for the T flip-flop seemed to be a little bit simpler than what we get for the D. That's not always going to be the case, but in this particular example, if we are using T flip-flops, it is simpler than the D flip-flop. Now, let's see if we can do this same thing for the SR and for the JK. So if we recall the SR logic, remember for an SR, you can have 0, 0 as your input, and that is maintaining whatever the current Q is. So Q plus will be the same as Q if S and R are zeros. And then if you put in 0, 1 for S and R, that is a reset, so the Q plus will go to 0 regardless of where Q is. And then 1, 0 is a set, and so you will go to 1 regardless of where the current Q is. And then in the case of the SR, we're not allowed to use the 1, 1. Now if we flip this backward, which we've seen before, in this case, going from 0 to 0 could be a maintain or it could be a reset, so that becomes 0 and R doesn't matter, so that becomes 0 and don't care. Going from 0 to 1 has to be a set. That's the only way to get from 0 to 1, and so our logic for S and R has to be 1 and 0. Going from 1 to 0 is a 0, 1 because that is a reset, and then going from 1 to 1 could be a maintain or it could be a set. So in that case the S logic doesn't matter, but the R has to be 0. So we have a couple don't cares in this map, and in order to implement things for S and R flip-flops, we have to look at our current Q and our next Q, and we have to put in a value for S and R in parallel. So let's go ahead and do that for SA and RA. So recall, this is our state, our binary state table, and then I'm going to put this just to help remind us of what the S and the R logic need to be. And thankfully I have animated this with a little bit more legible writing than my chicken scratch with the telestrator here. And so in this case we're going from the A to x equals 0, the A column, and so the arrows there illustrate what comparisons we're making. So in the first entry, the top row there, we have a 0 going to a 0, which means our S needs to be 0 and our R needs to be x, because we have a 0 going to a 0, and so we have 0x. Then in our next entry down, we have a 0 going to a 1, which means we get a 1 and a 0. We have a 1 going to a 0, which means we get a 0 and a 1. And then we have a 1 going to a 1, which means we get a don't care and a 0. Now we're going to transition to the x equal 1 column, still looking at the A's. And so in this case, our top entry is a 0 going to a 0, so that again is 0 don't care. Then we have a 0 also going to a 0, once again 0 and don't care. Then we have a 1 going to a 1, so that gives us a don't care and a 0. And then we have a 1 going to a 0, which gives us 0 and 1. And now we can look at this and circle our groups, and we get the logic that you see there. So the SA comes out to x prime a prime b. That poor little one doesn't have any neighbors that it can circle up with, and neither do the ones on the R K-map. And so we get x prime ab or x a b prime. Now we have to do the same thing. This is just deriving the logic for the SR flip-flop for A. We have to do the same thing for B. So let's do that again for B. And again we have our binary table and we have our logic for the SR flip-flop. And so we are going from B here. And so we have a 0 to a 0, that gives us 0x. We have a 1 to a 1, that gives us x0. We have a 1 to a 0, that gives us 0, 1. And we have a 0 to a 1, so that gives us a 1, 0. Then we move over to the x equal 1 column. We have a 0 to a 1, which gives us a 1, 0 logic. Then we have a 1 to a 1, which gives us x0. And then we have 1 to 0, which gives us 0, 1. And then we have 0 to 1, which gives us 1, 0. And this logic allows us to do a little bit of grouping. And so here we see the groups that we can make on those K-maps, and we get x a prime or a b prime. And then on the right hand side we get just a b. Now we're going to do the same thing with JK flip-flop. So JK is very similar, with the addition of the 1, 1 for both J and K is a toggle. And so the difference with the JK logic really are in these 0 to 1 and 1 to 0 transitions. The 0, 0 is the same exact thing as the SR. The 1, 1 is the same exact thing as the SR. But what you see here is we add this 1, 1 in both of these cases, because 0 to 1 or 1 to 0 could be toggles. And so the addition of that gives us, instead of a hard 0, now we have another don't care here. And right here, we have another don't care. So those don't cares that we're seeing on that map replace our hard zeros that we had before. And what we'll see as we repeat this with JK flip-flops is that gives us a little bit more flexibility in our logic, a little bit more simplification. So let's go ahead and repeat the process here. And so in this case, we're comparing our A to our A+, and I'm not going to do it for each individual column, but you can see this is what we have. We have a 0 to 0, which gives us 0x, 0 to 1 gives us 1x, 1 to 0 gives us x1, and 1 to 1 gives us x0. We can do the same thing for our x equal 1 column. We fill in this. You can see that these are the values. We have a couple 0 to 0s, which gives us 0 and x, and then we have a 1 to 1, which gives us x0, and then we have a 1 to 0, which gives us x1. And now, if we circle these groups, we see that we can get x prime b, and on the KA map, we can get x prime b or x b prime, which actually works out to be x exclusive ORed with b. And so if we recall the logic that we had if we used SR flip-flops, you'll notice that the JA logic is simpler than the SA logic. That allowed us to remove the A prime there, and that is largely because of this don't care that we see right there below the 1. That allowed for a bigger grouping. And then over here, when we used RA the SR logic. The RA logic up here was X prime AB, so we were able to eliminate the A variables in both cases, and that is largely because, again, of these don't cares here, which allowed us to make some bigger groups. We can move on to our B's. So we just did the JA and the KA, now we do the JB and the KB, and once again we're going to compare our current B to our next B here. So these are going to be the right columns in each of these sets, and so we have the logic that you see on your screen. 0 to 0 gives us 0x, 1 to 1 gives us x0, and then we have 1 to 0 gives us x1, and 0 to 1 gives us 1x. We do the same thing for the x equal 1. We have 0 to 1 gives us 1x. We have a 1 to 1 which gives us x0. We have a 1 to 0 which gives us x1, and we finally have a 0 to 1 which gives us 1x. And now if we start circling our logic here in the K-map, what you see is we have A or X for the JB, and then we simply have A for the KB. Now if you recall what we got for the SR flip-flop, we had XA prime or AB prime. And then for the RB, we had AB. So what you notice, and this is not a fluke, is by adding those don't cares, the final logic is simpler because we can make bigger groups on our K-map. And so this is why, and I emphasize this again, this may very well be a test question either on the final exam or test 2, the JK logic will always be equally as simple or simpler than the SR logic. And in fact, that is the reason that LogicWorks does not even give you the option of an SR flip-flop. And for your second project, don't think about using SR flip-flops because JK will give you better logic implementation in every possible case. So we cannot guarantee with T and D flip-flops that T is always going to be better than D or vice versa, but we can guarantee you every single time that JK flip-flops will give you equally or simpler logic, equally complex or simpler logic than the SR. Okay?